Welcome back, everyone. Many of you may recognize Tom Sandri from our previous conversation on workforce development. And during our last conversation, I had the opportunity to ask Tom about his favorite topic to present. And one that actually stood out to me was understanding the partial discharge field testing of shield power cables. Tom Sandri is a staple of the needle world who is currently serving as the Director of Workforce Development for Vector Power. Tom's career spans 30 years with roles in training, sales, product management, operations, and engineering with stints at some of the most well-known institutions, including Philadelphia Electric, Megger, Protec, Shermco, and now in his current role at Vector Power. Welcome back, Tom. And for those who may not have had the opportunity to see our other interview, can you tell us a bit more about yourself?
Yeah, as you mentioned, I'm 30 plus years, actually, emphasis on the plus years in the industry. And a lot of my background, during that time period was in the world of cables, particularly the shielded power cables. Back in the early part of the 90s, I was actually part of the Insulated Conductor Committee of the Power Engineering Society of the IEEE. And what was really interesting was back during that time period, a lot of the big controversy of what we called extruded dielectric, or the fantastic plastic cables, the polyethylenes, crossing polyethylenes. We were really learning a lot of revelation about how these cables age, and really putting some challenges on us as far as the testing methods that we had adopted. Like, for instance, DC testing and so forth. I mean, many of you watching right now probably have realized that DC has fallen from grace as far as a maintenance test on service aged medium voltage extruded dielectric cables. And it was during that time period that our big challenge was there was a bunch of new technologies, and the IEEE 400 document, which was for field testing of shielded power cables, the original only talked about DC. Now we're getting all these new emerging technologies. So basically the consensus was we were going to then turn 400 into an omnibus type of document. So 400, basically just talked about testing in general and kind of gave a preview as all the emerging and new technologies. And then it was kind of broken off into like 400.1 talks specifically about DC testing, but now only for laminated dielectric type of cable structures. 400.2 introduced us to and teaches us all about the world of very low frequency testing at 0.1 hertz. 400.3, which is kind of today's focus, really takes us down the field testing of partial discharge on the cable structures. Dot 4 introduces us to another fascinating technology called damped AC. And then dot 5, we brought DC back for extruded dielectrics. But what drove bringing the DC back was solar farms. They're using modern day extruded dielectric cables, and they're carrying DC. So dot 5 does not say, oh, it's fine to go test service age cables with DC again. Dot 5 basically says if you're using extruded dielectrics that are designed to carry DC, here's the testing recommendations.
Makes sense. And that's a great, like I said, it's very fascinating stuff. And this is going to be a bit more of a technical, not necessarily, I would consider this mid to intermediate advanced level stuff here. So if you're new to the field, feel free to sit through it with us, but this is going to be a little bit more on the seasoned technical aspect of those folks that are out there doing the shielded cable testing. So, and like I said before, our typical driver on this is kind of, I'll ask you questions, get an answer in response, but I am very ignorant to shield testing, and I'm not afraid to admit it. I'm not a technician, just a recruiter over here, and I'll own that today. So today is going to be not necessarily lecture specific, but I want to give Tom a platform to kind of spread the knowledge on this and hopefully bring something that's typically not at the forefront of the minds of technicians, and let Tom kind of walk through it and provide the data-backed discussion on this. And I believe it's going to be factory versus field testing is kind of what we're looking at. Is that correct, Tom?
Yeah, we're going to kind of take in the whole world and gamut of partial discharge testing for the shielded power cables. And kind of the unofficial title I always like to give to this is we're going to navigate through the truth, half truth, and myths
I love it.
associated with the testing.
Absolutely. I love it. And so this is my other caveat here is you're not gonna hear a lot from me. What I plan on doing on this one, I'm gonna give Tom the floor, and then I'm going to play as humanly ignorant as possible and bombard him with a bunch of random questions. And hopefully maybe provide a window of insight into those younger folks that may not understand the effects and the adversity there. And I'm going to try to keep up with the technical prowess of Tom. So without further ado, and that caveat being out there, Tom, I'm going to turn the floor over to you. And I apologize in advance for asking any dumb questions. There's not stupid questions. There's only stupid people. And I'm going to try not to be that guy. So
Trust me, any question that you ask that you deem to be stupid, there is probably going to be 15 viewers that says, "Oh my God, thank goodness he asked that question."
Thank God he asked it. Well, I'm going to try to, like I said, I'm going to keep it simple, stupid on my end, and try to be as inquisitive as possible because this stuff truly does fascinate me. And without further ado, I'm going to go ahead and turn over the floor to you, my friend.
All right. Well, why don't we just start, on the most basic, simple. What is partial discharge?
Absolutely.
Okay. Let's at least, get on a good foundation. And when we think about partial discharge, there is actually more than one form of partial discharge that we may encounter. When we talk about corona, and I'm sure all the viewers have probably, experienced this, a hot, humid day. They're outside, there's a pole mount transformer and you hear the crackling, hissing sound coming off the transformer. Under the right lighting conditions, you might even see a little bit of a purple haze. Sorry about that reference there, and yes, it is a legitimate cigar that I have in my hand and not one of those other ones. So we were not talking about Jimmy there.
No
but
drug test for you next week, right?
Yeah. Yeah, we were talking about the Jimmy version of Purple Haze, coming off of the bushings. So that's discharges to the atmosphere, relatively harmless, not really eroding or harming anything. Now, if there is surface contaminations, that innocent corona could turn into another form that we would refer to as surface tracking. So instead of discharging to the atmosphere because of the contaminations, maybe down the stress cone or whatever, we actually now start to get tracking discharging. And a lot of you probably, when you looked at insulators and you saw those little black, what look like carbon paths that look like branches of a tree forming unsightly, that's surface tracking. Okay.
Now, what are some of the things that would cause the surface contamination?
Oh, I mean, all of the pollutants in the air for one. And depending upon your industry, the products that you're manufacturing, building, the environment that it's in, aluminum mills come to mind quite a bit, because again, what do you have with the aluminum powder?
Exactly. Well, and that's one of those things I think to kind of to explain the scope, and we're talking microscopic levels in many instances, and particles in the air and things like that. Would that be correct?
Yeah, and again, high humidity, water molecules or moisture on the stress cones and everything, which again, like when we talk about metal clad switchgear and everything, the reason we put heaters inside there is not to give a comfortable, warm environment to the equipment, but to control the moisture inside the cabinet. Because again, water molecules or moisture accumulating is going to start to form that surface tracking. Basically, it's going to start to deteriorate the quality of the surface of the insulator. Instead of having the proper clearances, we're providing tracking paths for that current at that point. And then you also have, what they call, I hope I don't booger this one up. I just kind of refer to it as like phase to phase or discharges in the air. So like on a cable landing, if you have cables where on your cutbacks on your stress cone from where you now have the exposed high voltage to where your shield starts, if they're laid to where they're not even, you now have a high potential directly next to a low potential where the shield is. So you have discharging going from phase to phase, from high to low.
Gotcha.
I'll just call it phase to phase or air discharging,
Makes sense.
since I have a senior citizen moment and I forget the technical term for it.
Happens to the best
Okay.
of us.
I did say that, emphasis on the plus on that 30-year statement. And then probably the other one that, particularly when we're doing a lot of the testing of the cables on acceptance testing and so forth, void discharges. Void discharges typically is where, kind of picture you have a chunk of insulation, and inside the block of insulation you have a gap, a void, a gas pocket or air pocket. So the material surrounding it has a certain strength to withstand the voltage. The gas pocket is weaker. So as the potential rises, the surrounding material can withstand it, but charge builds along the void, and then it can no longer sustain, and it discharges through the void. Hence,
Gotcha.
partial discharge, only through the void, not through the whole insulator. But if this occurs and continues to occur, it's going to grow the size of the void. It's going to start to go into what we call an electrical treeing or growth. And at some point, it's going to basically provide a current path through the insulator, and you're going to have a total failure at that point. So
I have two quick questions, Tom, just so I can kind of set the base. So these cables, what are the applications, and where are we seeing this, and where is it applicable? Is it the cable runs to the back of a switch gear? Is it underground cabling? Is it transmission lines? Where does the partial discharge aspect of things, where is it most applicable, or is it for all of them?
Well, definitely for today's topic, it's going to be the shielded power cables. So the transmission lines, the aerials, pretty much are just, big open conductors and everything. There's really no dielectrics or anything up on that. But yes, these could be cables that are used for distribution of power. Okay. They could be cables that are just used to connect, like from transformer to breaker, and so forth. So anywhere in the distribution realm, they could be laying in conduit, they could be laying on trays, they could be direct buried in the ground. Gotcha. They would all form the shielded power cable world, where we're just basically connecting apparatus and everything together to get power from point A to load.
And it's primarily the medium voltage, high voltage applications, I'm assuming.
Yes. If you really look at characteristics of the void, the little hole, characteristics on that, typically you require at least around 2,000 volts to form charge and cause a breakdown. So normal practical application of partial discharge testing, we normally say 41.6 world up, to your extra high frequencies, etc. But like for your 480 volt cables and so forth, normally they will not experience this type of phenomena. I mean, when they fault, it'll just go straight into fault. So normally at 41.6 on up, we normally look at that as the world where partial discharge testing is applicable.
Gotcha. And this is going to be, like I said, I'm here to ask the stupid questions. But so what is the ultimate objective of partial discharge testing? I think we kind of floated by that, and I want to kind of why would a technician even need to do partial discharge testing?
Think of it as fault locating before the fault happens.
Gotcha.
So prevent the unscheduled outage, detect that the problem is there so you can schedule a corrective action. You control when that circuit goes down rather than leaving it to fate.
Gotcha. And so one of the ramifications, let's say I'm testing a cable and or I haven't even tested it yet. I have excessive partial discharge. How does that affect the end state equipment?
Initially it's not going to have an effect on the end state equipment, but if it goes to fault and all of a sudden we have a discharge of, maximum fault current, this obviously is going to put stress on the associated apparatus. If the protection equipment don't clear in their prescribed periods of time and so forth. Or like we have a direct bonded system. We're not using high resistive grounds or anything. Your transformers and so forth are going to take quite a jolt.
Gotcha. Okay, that makes sense. And is partial discharge testing, is that, well, we've already talked to the ANSI standards and all that. Is this one of those kind of things that is now mandated per new regulations, or is this just a recommended?
That is a very, very good question. I've read through the majority of 70B, the new, which is now standard. So the shalls have become, I should say the
recommended have become the shalls.
Right. But I need to kind of read and cursor through that a little bit. I don't think that the partial discharge is a mandated, although it is growing considerably in popularity, particularly on acceptance testing. We're seeing a lot of this done in the renewable world, because in the renewable world, whether it be the wind farms or the solar farms, these industries, they go out to bid for, lowest bid price. Not always the lowest qualified bid price, but lowest price. So, we've experienced a lot of premature failing in cable structures on wind farms, on solar farms. A lot of times it takes us down to craftsmanship issues where, while doing the termination or doing the splice or the joint, we got a little bit too careless with our left knife grooves in, which are voids and so forth. So we commission, we energize, and within our first 24 to 36 months, we're experiencing failures.
Gotcha.
Now, as far as when and to what level, in the IEEE document series, the 400, they do describe testing as installation testing, acceptance testing, and maintenance testing.
Gotcha.
So installation testing is where we would actually test the raw cable before splices and terminations are put on. So this might be like, for instance, we can either test it on the drum if both ends are available to us, where we can do our necessary cutbacks so we don't flash over at the flat cuts, or it could be after we've laid the cable into the trenches, but before we've started building the splices and the terminations. So the goal of installation testing is to make sure that the factory sent you quality product. It didn't get damaged in shipment. It didn't get damaged in the initial installation. And we know now the cable is good before spending all the time, effort, because these splice kits and terms are not
splicing,
cheap.
Terminating, and definitely not.
So acceptance testing is then basically carried out after the terminations and splices are in place, but before energization. Gotcha. So really at this stage, we can say, well, we know the cable's good. I did that during the installation. So really what I'm focusing in now on is the quality of the splices, the terms, and the workmanship in putting them all together. And then maintenance testing basically is anytime after you've energized, whether it's for a preventative maintenance, anytime that you bring it back down to retest after it's been energized, technically that would fall into the category of a maintenance level test.
And then one more point to this too, because I know a lot of the folks that watch this are very NETA centric, and I know that NETA works with ANSI. Is that partial discharge testing, has it made its way into the NETA ATS and MTS?
It is definitely in the new MTS that was just recently released. Matter of fact, I was actually on the ballot committee for the MTS and actually helped out with the working group that rewrote the whole section on cable for the MTS. Now, the ATS is up for renewal. Gotcha. I'm on the ballot committee for that one as well. But so we're still working on the 2021 revision of the ATS. It's still the original, where kind of when you get to the cable section, it's like, and here's the IEEE 400 document, go read and figure it out.
Gotcha.
Now, the new ATS is going to mirror a lot of what was accomplished in the recent release of the brand new MTS, 400, where that whole cable section has really grown and blossomed. I mean, now we talk about testing it at VLF, very low frequency. There's talks in there about testing it at power frequency, 60 hertz, near power frequency, like using what's called these resonant power supplies. And we talk more extensively about tangent delta testing of cables, as well as partial discharge testing. So the NETA documents, this last release on the MTS and what's going to happen in the new ATS, that whole section has just become very, very information rich.
Gotcha. Awesome. Now, do you find that there's enough information in the NETA MTS now that you don't necessarily have to refer back to the ANSI 400? Is it encompassed, or would you still suggest that techs actually go back and read the ANSI documentation?
Well, I always recommend having, the ANSI or the actual IEEE guides, because obviously they go into a lot more background, a lot more. Again, in the IEEE, they'll actually take you into the measurement methodology and so forth. In the
Gotcha.
NETA guides or the NETA standards, we assume that you already know how to perform. So this is more of kind of a checklist of what you need to be doing and reference to what quantifies good, dubious, or bad in your reading.
Gotcha. Perfect. And I'll let you get back to the presentation. I just had those I wanted to get out of the way that were sitting at the top of mind, and I'll forget them before you let me. So,
Oh, no worries. So obviously, in the world of partial discharge testing, we actually have two completely schools or disciplines where this takes place. One, it's a quality control program that most of the cable manufacturers, or I should probably say virtually all the cable manufacturers, perform partial discharge testing on their cables during manufacturing process and on whatever their shippable lengths are going to be. They will run partial discharge testing in order to ensure that they are sending out a quality product.
gotcha.
The component manufacturers, the manufacturers that specialize in doing the splices or joints or the terminations, they also do partial discharge testing at the factory level to ensure that their product is good before it goes out to the client or end user. So you have I'll just call it the factory world of testing. And as you can imagine, in the factory world of testing, they don't have as many of the obstacles that we face in the field. Generally speaking, in their world, not almost all of the testing is traditionally done at power frequency, 50 or 60 hertz. The size, and the weight, and construction of the power supplies in order to energize these cables, to the recommended voltage levels is not a hindrance to them at the 60 hertz level. They've got the real estate, the room, and they don't have to move this equipment around.
Right.
It's not like, two technicians are going to pick it up at the end of the day, try to fit it in the back of their truck and haul it to the next job.
Right.
It's going to stay in place. So they get to operate under a very controlled environment, under very controlled conditions. Now you have the discipline that is adopting it and using it in the field. In the field, we've got a lot more obstacles. So when we talk about field testing, you'll see references made in the literature. IEEE 400.3 is the particular guide that I want to kind of focus on. In there, they will talk about the different ways that we can supply test voltage. So we can supply test voltage using 60 hertz. But one of the problems that you run across or limitations you run across with 60 hertz testing in a field environment is the size and the weight of the equipment. Now, why does this come into play? When you think of a cable, you've got a conductor and you've got a metallic shield, okay? They're in parallel with one another. In the middle is the dielectric. So basically, you formed a capacitor.
Yep. Makes
Now,
sense.
when you look at lengths of cable, surface area of those two plates and the bulk amount of dielectric gets pretty large. When you're looking at 1,000, 2,000, 7 miles or whatever of cable, you're looking
runs.
at big capacitors. So we really have to look at the reactive element of capacitive reactance and what effect this is going to have on your power supply. Now remember, at power frequency, let's just say we want to energize the cable to 22,000 volts. I've got to go from 0 to 22,000 volts in, 4 milliseconds?
Very fast. Yep.
That's pretty fast. So in 4 milliseconds, I've got to charge this huge capacitor that rapidly. Well, that's going to take a lot of what they call volt-amp draw off of your power supply. So the VA size of the power supply gets very, very large. In some of my presentations, I break the mathematics down where if you want to first learn what the capacitive reactance is, you would use the formula 1 divided by 2 pi FC. Pi, as we all know, is the standard 3.14, blah, 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 blah. 2 pi, 6.28, blah, 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 blah. F is the frequency of the applied voltage.
C is the capacitance.
So we could put 60 hertz in there. And C is the capacitance of the cable specimen that I'm going to test. So let's just say we were doing 15 kV cable of about maybe 1,000 to 1,500 foot. Capacitance of that cable is probably going to be around 1 microfarad. If we plug all of the numbers into that formula, 1 divided by 2 pi FC, and we use 60 for frequency, we're going to come up with a reactance value of 200 some odd k ohms of reactance, capacitive reactance. Now, if I want to calculate my VA, I just again use Ohm's law. I take my voltage and my applied voltage and my ohmic structure reactance. So take my 22,000 volts divided by the 2,000 whatever I calculated on my reactance. And that's going to tell me I'm going to need to draw somewhere around 8.3 amps of current from my power supply. Now, VA is just volts times amps. So if I take 8.3 amps and now multiply that by the 22,000 volts, I need a power supply of about 183 kVA.
kV, yep.
That's a distribution transformer.
Yeah, absolutely.
And
now you're looking at hauling that around to actually conduct the actual freaking test.
Yeah, and unload it from your truck and carry it up on a catwalk.
Good luck with that.
No problem, man. We can get her done. So obviously this in itself becomes, in some cases, a no-show for some people. And the other is okay, it gets out on the job site. What power supply do you have that I can plug this into to energize 183 kV transformer? So there are some limitations to what you can do here. Now, we can miniaturize the equipment by going to what they call near power frequency, where if we have too much capacitance, we use inductance to dial down the capacitance of the cable. And in the near power frequency, the reason we call it near power frequency is depending upon the tuning, you can have anywhere between like 30 hertz up to around 100 plus hertz. So it's still in that power frequency realm, hence near power frequency realm.
Right.
It brings the size and weight of the power supply down a little bit better. But I mean, you are normally talking about still installing it into a dedicated vehicle is still something that I'm not going to.
You're not going to be humping it up, like you said, on skiffs and steps and all that. You're definitely going to have it. Right. You could probably maintain the power source in a truck or a trailer and then run the cabling to do the test, which I'm assuming is probably how it's being done now.
Exactly.
Gotcha.
And then one of the big revelations was, in order to create partial discharge, we need an alternating polarity. Okay. We can't produce partial discharge with direct current or DC. So when the very low frequency or VLF power supply started to come out into the industry, this was another big revelation in really making field partial discharge more available to the masses. Because let's go back to that same formula of 1 divided by 2 pi FC. Instead of using 60, let's use 0.1. We still use the same microfarad of capacitance. We go through the calculation, and we now get a capacitive reactance of around 1.6 megohms. Gotcha. We go through the further math, of 22,000 volts divided by the 1.6 megohms. Now we see we're only pulling about, a fraction of the current off the power supply. I think like around 303 VA. is what we're going to be pulling from the power supply. So the test equipment just became really small,
substantially smaller, absolutely
portable, and to the masses a lot more affordable as well. So the 0.1 hertz testing has become very, very popular. But as you can imagine, with all these different techniques, all these different methodologies, there are pros and there are cons associated with it. In the perfect world, we would just do it all at 60 hertz. I mean, that's what the circuit's going to operate at. But in the practical world, the 60 hertz approach might forebode a lot of organizations from embarking upon the technology. I can't get the equipment where I need to get it. I can't afford the test. It just, so in the 400.3 document, it talks about the power supplies, and it talks about what they call alternate voltage sources or alternate power supplies, where like this damped AC technology, the VLF or low frequency technologies and all get categorized as the alternative to power frequency. And then you have the near power frequency and the power frequency varieties. Right. Everyone, and this is why, again, I recommend, even though the NITA has done a tremendous job, get a copy of the 400.3, get a copy of the 400/2012 revision, because it really breaks down all the different power supplies and talks a lot about the pros and the cons.
Now, so damped AC is a new one to me. What is damped AC?
Damped AC is a very fascinating technology. Basically, what it does is it uses the small, lightweight portability of a DC source, but it has a resonating inductor on it. So once you reach your peak level, you strike the resonating inductor and it sends an oscillating blast out into the cable. So it starts oscillating high and then damps down to zero. Hence the name.
That's cool.
Damped AC.
Yeah. I'll be damped is what I said, folks. I'll be damped, not damped.
Yeah. It's cool. Very fascinating.
Yeah.
And it actually has its own IEEE guide. IEEE 400.4 speaks entirely on applications of the DAC or damped AC technique, although very partial discharge is one of the utilizations for it. So first, we have to recognize that we are operating in two totally different environments from a factory. Size, weight, cost at a factory where my product is cable and, I'm going to get my return on my investment and et cetera, et cetera, et cetera. I'm not going to be moving it around. There's certain things I can do in that environment. In a field environment, we already talked about the one, potential obstacle that I have to navigate is what is the most practical power source that I can use for my test voltage? What are my real world limitations, and what is my most practical approach as far as just the hardware, the power source. But now also keep in mind in the field, when we talk about partial discharge, we're talking about very, very small levels of measurement. We're talking levels of measurements down into the pico and the nano and micro levels. Okay. These are tiny, tiny, levels of measurement. And a little bit off color. Hope your viewers and everything can take a little bit of off color.
Absolutely.
But They're tough. The factory, one of the measurement sensitivity levels is what they call 5 picocoulombs. Coulomb is a measurement of charge, movement of charge. So in partial discharge, we talk about the movement of charge. Okay. So 5 picocoulombs would be a sensitivity that they would measure in a factory type environment. Well, here's the off color. If you want to put this into perspective, a North American gnat flatulates at approximately 4 picocoulombs. So you're only 1 picocoulomb above a gnat fart.
That is the best scale reference I think I've ever heard, Tom. So I'm here for it. I don't care what anybody else says. That was awesome.
Hey, 4 years of engineering school taught me that.
There you go. That is fantastic.
I can put it into technical terms now.
I like it. I like it. Well, I think it's very, very important to point that out. So, but just by the variability, like you said, in a factory environment where this is all you manufacture, you know, limit climate or control climate. You can control, you know, the air around it. You can filter it. You can do all that, and you can introduce this. But when you get out in the field, there are no control methodologies for that stuff at
Right.
all.
One of the
So,
problems that you face in the real world, in the field, is noise.
mhm.
Now, these discharges basically create these transients that will oscillate on the cable, and that's what we're trying to pick up and measure with our equipment in order to get a quantitative value of magnitude and repetition rate and so forth. Now, these signals are already, as we already discussed, I mean, you know, we're dealing with NatFart level of measurement signals to begin
Absolutely.
with. And in the outdoor world, there's a lot of other sources of high frequencies that can get into the measurement circuitry. So now it's kind of looking for the proverbial needle in the haystack. You know, you've got to cut the hedges down low enough so that you can see across. Okay. If the hedge is high, you know, if my hedge is, 3 feet high, I'm only going to be able to see the head of a 4-foot person. Okay. They've got to stick above the noise for me to be able to see them. So noise control or noise mitigation becomes one of our obstacles in a real world environment. In a factory environment, we can use things like ferrite cages and so forth, and we
Right.
can really control the noise in
Right.
these environments. Now, one of the other issues that you have in the real world, because at a factory, when they test the component or they test the cable, they're only testing cable at shippable lengths. Okay. And the cable doesn't have splices and terms and everything
Right.
on it at this point.
Right.
And they're in controlled shippable lengths. Okay. So again, we have that control factor going. These transients that are produced, these signals that are being produced, they're high frequency in nature. I mean, they're up in the upper megahertz bands.
Okay.
Now, a cable, there's a reason why the electrical utilities, you know, deliver 60 hertz power and they don't deliver high speed internet. Power cables are low pass filters.
Right.
They absorb the high frequencies and tend to pass the low frequencies. So in the factory, they're not concerned with mapping a location of where the PD is being created. Okay. So they can test from both ends of the cable and they're just looking for the presence of, but they're not necessarily trying to capture these signals, measure time delay between reflections, and mapping. The problem you have with mapping on an electrical power cable being a low pass filter is, one, you have attenuation. Okay. So as the signal travels, again, think of mileage in your car. Okay. The sticker when you bought it says that you're going to get 35 miles to the gallon, but you're driving on a very rough roadway on a 20% upward incline, and there's a 30-mile-an-hour headwind. You're not getting 35 miles to the gallon. Sorry to
Not at
pop your
all.
bubble.
Right.
Okay. Your mileage will vary. Okay. So with the attenuation, depending upon the length of the cable, how many splices and everything that may be there as it's absorbing this signal and so forth, you may not be able to see the whole length. Okay. And remember that partial discharge, when it occurs, pop, transient shoots both directions. One shoots directly toward your coupling equipment, passes the coupling equipment at time period 1. The other pulse fires off toward the other end, reflects off the end of the cable, and now has to have enough energy to make its way all the way back to the receiver.
Yep.
If it doesn't make its way back, if it attenuates and burns out, you can't do mapping because you don't have the two pulses any longer. Okay. Right. Another aspect is called dispersion. So as the cable starts to absorb this energy, the reflected images, not only do they attenuate, but they stretch out and elongate through this phenomenon called dispersion. Sure. So again, when you're trying to meet, a factory specification of like 5 picocoulomb, accomplishable in the way they do it in the factory, and they're not worried about doing mapping, and they're doing it on controlled, shippable lengths of cable. Now, you go out to an average wind farm, and you go to the collector feeder home run section from the last turbine down to the collector station. That might be 5 miles, 8 miles, 10 miles, 15 miles of cable.
Right.
Do you think that's all one piece?
No, they definitely spliced it. And then and so that's one of those things. And I guess even with a perfect splice, is that picked up? Is there typically going to, are you going to be able to identify that through the testing of partial discharge? Or is it like I said, this is all new to me on the partial discharge. Are you trying to do it? Are you actually doing the full test run of the 15 miles at that point and trying to pick up the minutia in there?
Well, this is one of the real world obstacles that you run across. In some constructions, they might have several junction boxes.
Mm-hmm.
So if they have junction boxes and they're on the surface of the ground, if I'm not, when I'm doing my initial calibration, what I do is I have a little pulse calibrator. I inject a known level. What I'm looking to see, can I see the full length of the cable and get that reflection back?
Right.
That's one way that I'm determining my sensitivity of my measurement. Now, here again is where this 5 picocoulomb sensitivity level in a field environment really falls apart.
Absolutely.
Because, again, what is the length of the cable? In some situations on cables that I was on, we had to go up to 500 picocoulombs or even, 1,000 picocoulombs in order to have enough pulse to make its way all the way down and make its way all the way back. Okay. Your mileage will vary.
Right.
Now, if you've got junction boxes and they're on the surface, what I might do is say, okay, I can no longer test the entire 7 miles. But I've got 2 junction boxes out there, so I can, or 3 junction boxes, so I can go to them, isolate the cable off of the junction box and bring it down into smaller segments. Mm-hmm. That obviously is going to be helpful in making sure that I can get the lowest sensitivity for the length of cable that I'm, going to be measuring on. Now, in some situations, all the splices are buried in the ground. They're not brought up to the surface. So what are you going to do? Trace, locate all your splices, dig a hole, tear apart your inline splice, and isolate?
Right, just to do the test. All you're going to do is introduce more issues.
You're not going to do that. So on some circuits, again, depending upon length, your sensitivity is going to vary because remember, that high-frequency pulse that's being created has to do a round trip. Right. It's got to be able to reflect all the way to the end and make its way all the way back to the receiver. If it doesn't come back to the receiver, we can't do a mapping on it. We can't tell you.
You won't have anything to measure. So how are you going to know?
Exactly.
Now, quick question too. So you said some instances have junction box and some don't. They may be buried and spliced, and you have to go and do a literal trenching out to go try to, make a measurement happen there. Why is there no efforts to standardize having junction boxes at X amount apart to where it will allow for that, or is it cost prohibitive, or does that make sense? Like, from a testing perspective, it would seem like you'd want to have junction boxes so you could test specific levels.
It's interesting. Like a lot of the design is to be cost effective for the installation, the cost of getting it up and running and so forth. And I will say that a lot of times the design engineers don't plan or think about maintenance and upkeep. Okay, they're delivering a cost-effective solution to your budget, what you're willing to spend, et cetera, et cetera.
Yep.
But they're not necessarily looking. Now, if in the bid spec to the engineering firm is that, you want to also make provisions for future preventative maintenance and this, that.
Right.
So we want to make sure that, we have junction boxes where if we have to, we can divide and conquer, or bring it down to smaller sections. Really comes down to what's your budget, how much are you willing to spend?
Right. And the designer during the bid process, make sure it's included in your scope of work if that's something you desire for future proofing, basically.
Right.
And to me, it kind of makes sense, because you're going to be able to isolate if you have the junction boxes. And again, like you said, and I had a conversation with a gentleman by the name of Vivek Karki, great dude. I don't know if you know Vivek, but he's with IPS. He's both an engineer and a field service technician. And he spoke to that, and it really is because the engineers oftentimes live in their little box over here and have never experienced the field aspects of it and don't realize the ramifications down the line. So
Oh yeah.
definitely see a lot of that. But to me, like just from a layman's perspective, as my perspective is today, it would only make sense and it would make troubleshooting astronomically easier if you had set junctions instead. I mean, now if you find an issue, you don't have any way of isolating that unless you have the junctions for distributed runs. And now you may have even a more costly repair and having to replace the entire freaking cable.
Oh, absolutely. And we've been focusing on like the renewables, which tend to typically fall under the jurisdiction of the utilities. Now, utilities, the cables that they tend to use are the cross-link polyethylene or the tree retardant TRXLPE cables, and the metallic shields are typically stranded wire concentric neutrals. Now, those stranded wires hold up pretty well over time. They form good conductors, relatively low losses and everything on them. So being able to see these very low-level signals through long distances is not that difficult to accomplish in those environments. But there's a whole other industry sector out there that is interested in partial discharge testing. The big industrial and commercial facilities, the refineries and the petrochemical plants and the pulp mills and so forth. Now, this industry tends to use a cable that is, the dielectric is ethylene propylene rubber, or EPR, which has much higher dielectric losses by design, by intent, than a polyethylene cable does. Also, the shields that they use tend to be what we call the ribbon or tape shields. That's that real flat, thin copper, and it's wrapped around the cable dielectric, okay? So you get these overlapping layers. Let me get that on frame. So you get these overlapping layers, okay? Well, these overlapping layers basically form a lot of inductance. As we learn from theory school, inductors tend to pass low frequencies and block high frequencies. What is the nature of the transients we're trying to measure? Up in the several hundred megahertz band.
Right.
So even before I talk to an industrial, hey, Tom, we'd love for you to come out. We've got this open paycheck right now. We're willing to give you to go ahead and do PD testing on our cables. First thing I say is, whoa, slow down. I don't even know if you're a contender for the technology. You're using ribbon cable or ribbon shield cables, tape shields. When's your next scheduled outage? And what I'll do is I'll go out there either with my pulse calibrator and equipment, send signal in, see how far I can hopefully imaginably measure on these type of circuits. And or if I don't want to take the full PD kit and the pulse calibrator out, there's another great little tool out there called a time domain reflectometer that sends high frequency pulses into the cable, slightly lower frequency band, but close enough to at least allow me to see how receptive is your circuit to high frequency transmissions.
Makes sense.
If it passes the TDR test, now I can manage my client's expectations, and in good faith, if I take his money, I've got a pretty darn good feeling that I can accomplish what I set out to accomplish, and I'm not ripping them off.
Absolutely.
So
now, a quick question too. I'm injecting here. Why do they choose to use a different cabling methodology in those plants and things like that? The rubber based over what you would see in the others.
Now, the insulation type, I definitely have enough experience in research and everything to know that. Let's go back to the whole concept of partial discharge. Remember the void discharge, builds charge, breaks down in the void. Okay. So what if I design the insulator, the dielectric material, intentionally lossy? So basically, I'm going to give you a paper cup, and you're going to fill it with water until it overflows. Discharge. Okay. Now I'm going to give you the same cup, but what I'm going to do is perforate it. You sit there filling. It never gets up to the brim or discharges because you're bleeding out the charge. So by making the dielectric lossier, the intent is we bleed the charge through larger leakage current, but we don't build a charge and allow it to discharge or spark over.
So it's literally just a mitigating circumstance. You're trying to get it to where you don't actually reach the point of partial discharge, basically.
Right. So in a lot of these designs, we'll actually see terminology like this is a PD resistant design. It resists the PD because it bleeds the charge. It doesn't form the charge. And now, why doesn't the utility company use it? Well, they're in the revenue business. A leaky cable costs money. Earthworms don't pay for their electricity. Okay. So they want something with very, very low dielectric loss. They're in the business of making sure that current gets from point A to point B in the most
especially
effective
with
manner.
The wheeling and everything else. So they're going over some substantial distances there. And I can imagine that would cause some issues.
Now, to a large industrial with their, notably shorter cable lengths and abundance of cable that they use, the extra losses is not a big deal.
Right.
In their world, they're looking for a more resilient, because again, talk about an order of magnitude harsher environment that they're putting them in.
Absolutely.
Because you might have ammonias and oils and all different types of contaminations depending upon, what the product is that this industry is producing. So they want, a real resilient. Now, in the nuclear industry, they were some of the earliest adopters to the ethylene propylene or EPR cable structures for the reliability of the nuclear plant, and particularly when you talk about the amount of moisture. I mean, what is a nuclear plant? It's the most expensive hot water heater you'll ever spend money on.
Facts. No, that's definitely a spot on, and that was one of those that just I've been holding that for like 3 minutes, so I'm trying to kind of work that out in my head. But it really does come to the atmospheric concerns or the environment, really, and like you said, they're not in the business of distributing power. They are literally there to make sure the equipment stays on. So you want a more resilient product, basically.
Exactly.
Okay, that makes a lot of sense.
And kind of moving into the worlds of truths, half truths, and myths associated with the technology. As you can imagine, this technology is becoming more and more popular because the concept of predictive maintenance, no longer preventative where, X amount of time has gone by, I'm going to take the circuit down and test just because, the clock tells me I should do so. But now I want to do predictive measurements. I want to find faults before they become faults. And I want to be able to schedule now my maintenance accordingly. So obviously, this is very attractive.
Absolutely. I can imagine the cost savings are phenomenal at that,
So a lot of people are very interested in this, world of partial discharge now. And here's where, who was the gentleman really noted, he would always tell a story and then he would say, and now for the rest of the story.
It's not Walter Cronkite, I don't think,
no,
is it? No, I cannot remember.
Somebody Harvey, was it?
Maybe. I cannot damn remember, Tom. I can't even age myself that much.
All viewers out there, when this is put on LinkedIn, put that in the comments. Paul Harvey, I think.
Paul Harvey, yes. You are right. And now for the rest of the story.
So
I'm with you.
What I've been finding is a lot of the marketing and sales hype that's out there tells a part of the story, and depending upon and again, any of you OEMs that are out there that manufacture test and measurement equipment and everything, this is not a slight against you, okay? This is not a slight against you, unless you take it to the extreme.
Right.
But obviously, you have an objective. You want to sell your solution, okay? Maybe you're a test company and you have invested all this time and money in the 60 hertz. You've invested maybe all the money in the near power frequency. You invested all the money maybe in the 0.1 hertz world. Okay. So obviously you want to win the contracts. You want to convince the client that yours is the best technology.
Absolutely.
Okay. There's nothing wrong with that as long as you're honest and tell the rest of the story. Okay. Right. Let the buyer take in the information, become an informed buyer. They can look at the pros and the cons and see what makes best sense for them, their budgets, their environment, where you're going to be doing the test, the types of cables that they're going to be testing, etc. make them an informed client and let them make the decision that best meets their needs. Okay. Manage the client's expectations.
Absolutely.
So in one form, we don't tell the rest of the story. Oh, we only want to do the 60 hertz or the near power frequency testing because part of the test is we look for partial discharge inception voltage. How much voltage does it take before PD is actually produced? The only accurate way of doing this is at 60 hertz. How it's going to
Because
react
that's where
under
it's done in the
normal
factory.
operation.
So how are you going to know? Yeah.
Now, there is a tremendous amount of truth to that. And I say, yeah, you are right. Okay. Because at 60 hertz, your polarity reversals are very fast and sharp, like around 4 millisecond timelines, right? Okay. So you don't have a lot of bleed down time. Okay.
Right.
You go from 0 to, Mach 1 in 4 milliseconds.
In the 4
milliseconds
milliseconds
and so forth.
for the,
so
for
you
the
build
frequency.
charge quickly, boom, snap. You get a good perspective of your partial discharge inception levels. Okay. Now, one of the sales stories that I'll tell you, if I'm pushing this technology and I want you to buy into this technology, okay, I'm being truthful with you. This will give you a clear picture of how it's going to operate under normal operating conditions because you're running your circuit at 60 hertz. Stay away from that 0.1 hertz, man. Oh my God, stay away from it. The partial discharge inception voltage will not correlate to 60 hertz because of the loss factors, because in an oscillatory sine wave, the ramp up time and the polarity reversal time at 0.1 hertz is very elongated. So what's happening is you're bleeding charge through leakage current. It's going to force you to go higher in overall magnitude to build the charge and get a flashover or discharge. So your PDIVs are going to be much higher than in the real world, giving you a false sense of security that partial discharge only occurs all the way up here, when in reality it might be occurring here. There is truth to that. There is absolute truth to that. However, Paul Harvey and the rest of the story. 1, if it is a brand new cable, installation or acceptance testing, the void does not have any contaminations in it attributing to those extra losses. Okay. So your PDIV in a acceptance and installation, even at 0.1 hertz sinusoidal, is going to correlate very closely to its actual performance at 60 hertz because we don't have the contaminations inside the gap. Now, if you bought your cable from Joe, the bargain basement cable seller on eBay, all right, all bets are off.
Right.
Okay.
Now you can definitely have some contaminants in the air gaps and things like that. So.
Okay. Now, with service age cable that has been in service for a period of time, there may have been periods of time where partial discharge was initiated. So there might be semiconductive residues inside the void, which is going to definitely add to the bleed off factor. So definitely now with those sinusoidal long transitions at 0.1 hertz, it may force me to go significantly higher, in which case my PDIV or inception voltage no longer correlates to the world of 60 hertz. However, if we read deeper into the IEEE 400.3, did you know that VLF actually has 2 distinct waveforms? One is the sinusoidal waveform. There's another one called the cosine rectangular, where basically what we're going to do is we're going to use a resonating switch. We're going to give you 5 seconds of positive DC, flip the polarity, give you 5 seconds of negative, flip the polarity, give you 5 seconds of positive.
So you're kind of making your own AC at that point?
You're making your own AC by alternating the polarity.
Interesting.
Now, the switching transitions are in the magnitude of 4 to 7-ish milliseconds. Nice and fast, just like your 60 hertz.
Right.
So there is a technique out there. One of the terminologies I've heard for is called the slope technology. It uses cosine rectangular with these fast polarity reversals, all of the white papers that I've seen from the European community on testing and side-by-sides at 60 versus cosine rectangular, they're showing gorgeous correlation to the 60 hertz test results. So there's the Paul Harvey rest of the story. 0.1 hertz on new and acceptance, cosine rectangular or sinusoidal VLF, totally cool for the reasons I explained. Service aged, okay, you may want to steer away from sinusoidal VLF, but the cosine rectangular
can work. Yeah, I guess it would
work
because it's artificial in nature and the swapping is going on. So because the equipment, I'm assuming that the injection equipment is literally doing that already.
Cost.
So then of course we know that the benefits of using the DC in that aspect. So now what would constitute being service age cable? What's the typical life expectancy and when would that become a problem?
In the IEEE guides and, well, almost all the literature now, we refer to service age once the cable has hit 5 years.
Okay.
Where did this number come from? Well, in the Insulated Conductor Committee, a lot of it was, and granted, take this with a little bit of grain of salt, because remember, in the Insulated Conductor Committee, a lot of the members and contributors and everything really come from the utility world. Gotcha. So a lot of the data samples and everything that are always sent in
are utility based,
are very utility based, and we already know that they tend to prefer the polyethylene structure, not the EPR structure.
TRX or the right.
So the service age was basically at what point has the dielectric age to where it's now starting to show evidence of the water treating,
degradation or water
saturation. And 5 years, just, based on the data that was brought in, seemed to be that reasonable number. But again, depending upon your environment and the way you run your cables, the environment you put the cables in, they could reach service age earlier. They could potentially reach service age later. I mean, what is your actual load, the environment they're being put in? One of the studies that I did on one wind farm, they were having a bunch of premature cable failures on this one feeder. And it was kind of interesting because during that time period, I was working for another service company, just for protection of and everything. I'll just leave their name out of it, but good, reputable company. And we got called out on an emergency cable fault locate. So we went out, we found the fault, repaired, and shook hands, and off we went. Well, it wasn't much more than 3 months later, they call again. They have another failure. Oh my God, it's on the same feeder. So we rush out there, and it's in a different location, but another splice had failed on this collector feeder. So at this time, when we excavate it, I said to the client, I said, I'm a little bit concerned because this is two faults. The first one
on the same
occurred 27 months after your acceptance test. The second fault happened 3 months from when we found the first fault, and again, it's in another splice. Would you mind if I take the splices? So we changed, the splices on all three phases. Would you mind if I took these splices back to my lab and did a little bit of an autopsy investigation on what's causing this? Well, the first thought was, oh, you hired a fly-by-night contractor. They did a really bad job with the splicing. I was expecting to see the evidence of knife cuts, misalignments of the splice body. I was looking for a bunch of human error.
Right.
Much to my surprise, it was built exactly to the instruction sheet. It was built very well. What I did find was extreme thermal degradation. I mean, if you ever looked at the dielectric insulation on a cross-linked polyethylene cable, it's very, very almost like translucent to white in color. This was charcoal gray to black in areas, and if you squeezed on it, it actually was mushy to the touch.
Really?
Extreme thermal degradation. So now it bodes the question, why are these cables overheating so bad?
Absolutely.
So we immediately go back to the owners of the wind farm, and it's like, hey, can you provide us some load data? What type of load currents and everything have these cables been exposed to? no greater than about 550 amps, well within the design spec of the
Right.
cable.
That's
So
not what I
now we're all
expected to hear.
scratching
I
our
thought
head
it was going to
going,
be overcurrent.
yeah, so we're scratching our head going like, all right, it's not overloading. Where's this heat being produced? Well, not to draw this on indefinitely, I kept on with my research, kept asking the whys and whys and whys. Finally, I came down to a paper that was presented in Arizona at one of the installation committees meetings back in, I think it was 2006, by a company called Geotherm. They specialize in thermal backfill. I learned so much about dirt,
I bet you did.
the quality of the dirt, and how
Yeah.
it radiates
Expands,
heat through it.
contracts, and right, and limits like the
Well,
thermal properties of the actual
right.
material because it's almost like an insulator itself if you think about it.
Exactly. So what you want is you want a backfill that has good thermal resistivity properties because the cable is going to heat under load.
Mm-hmm.
So, and you want that heat to dissipate away. So the design spec basically said that native soil could be used, but it had to be ground down to a certain particle size and it had to be compacted to a certain pressure level. Well, this was not done. So what was
Sloppy
happening,
man.
it was very porous around the cables. So
Mm-hmm.
think of a quilted blanket. All the heat gets trapped in those pockets.
Mm-hmm.
So think of a marathon runner. Normally, you can do a 10-mile, 20-mile marathon with no real effort. But now I'm going to go ahead and put you in a wetsuit and a
Right.
Alaskan Parker. How far are you going to get before you pass
Not
out
too
from heat
damn far.
exhaustion?
Yeah,
So
absolutely.
if you don't have the ability
I'll
to
be
release
there.
the heat, you overheat and burn out. And that was what the actual case was.
That's
And
wild.
also, this is why during the acceptance testing, it passed with flying colors because the splices were built well.
Right. Makes
There was
sense.
no partial discharge or anything due to craftsmanship issues, but the cable still failed because the environment we put it in was
That's
not supportive of an extended life on it. We weren't allowing these cables to
they're not
breathe or
dissipating
dissipate
heat.
heat.
Right.
We cooked them.
Right.
Um, so these are all different things that, when you spend time in the field and in this craft long enough, you know, you learn. This is called experience,
Absolutely.
what you start to pick up. But kind of going back onto the topic of the partial discharge and the truths, half truths, and so forth. There are truths in what we're hearing out there, but we're not getting the full stories.
Right.
Again, the 60 hertz, I'm all for it when it's practical. Okay. But there are a world of clients and environments and so forth where it is just not practical or cost prohibitive.
Would you
Okay.
say that's typically probably more often than not, I would imagine, just based on the cost and the scope and the logistics of trying to get a test set out there, depending on the length of the runs, it's so cost prohibitive at that point, I would
Oh,
imagine.
exactly. So if you got deep pockets, and price is not an issue to you, absolutely, it's a great way to go. And then, the rate that I'm going to have to charge you for it is going to be much higher because imagine my overhead, the cost of running that truck. It's a dedicated vehicle, a single
Right.
purpose vehicle. Okay. So my overhead's higher. I'm not going to absorb that. That's going to get passed on to the client. Again, there's nothing unethical about that. That's just called business.
Right.
Okay. But there's going to have a higher cost structure and everything in it. Now, if there's an alternative technique like the cosine rectangular, where now I can throw it in the back of a service
Self-service
truck,
vehicle, basically, yeah.
haul it out there. The power supply that I'm running it on could be just a standard diesel generator or a truck inverter, and I can run the same test. All right, I've just opened the market to a whole lot, a whole new buyer list. Okay.
Right, absolutely.
And like I said, on all these white papers and everything, and in Georgia Tech, and I forget what NEAT-TRAC, the acronym, what it actually breaks down to, but NEAT-TRAC did a study of all of these different technologies, which basically, warrants that they all have legitimate claim. But like anything, there's pros and cons associated with it. IEEE 400.5 does a gorgeous job of walking you through all the different technologies and giving you the pros and the cons. Now, again, going back to the factory versus field, I have seen in some of the bid specs and everything out there where it says that the testing has to be done at 60 hertz and it has to be done to a 5 picocoulomb sensitivity level. And I have a real struggle with this from a practical standpoint.
Absolutely.
And not a struggle in the sense that, oh, I can't bid on those jobs. I don't have a dog in this hunt. Okay.
Right.
I do a lot of consulting work, but I'm not out there trying to sell partial discharge testing. So I don't really have a dog in the hunt at this point. But I look at these bid specs and I'm saying, you're making a very unrealistic claim out there. So I'll give you the benefit of the doubt because, again, in the factory, we already talked we can control the noise factor. So we can get down to that gnat fart, okay, in a factory environment. I'm testing either just a component or I'm testing just a shippable length of cable, okay, a controlled length in a controlled environment. And I'm not doing mapping. So I'm just detecting presence of, okay? So meeting that standard or meeting that requirement in that environment, okay, makes sense.
Right.
I control all the factors and I can be reliable and repeatable in it, okay? Now I take this out into a field application. Well, one farm I go out onto, I've got a 3-mile collector feeder. The next one I go out to, I got an 8-mile. The next one I go out to, I've got 20 miles or whatever. Mm-hmm. I can't control the lengths. I can't control the number of splices.
It's all geographic in nature, basically. Wherever the array panels are and how they're fed back to the feeders, that's what's got to be.
Right. And, okay, I'm going to give you the benefit of the doubt. Let's say that in the noise cancellation, let's just say that you've concocted a phenomenal noise mitigation technique and filtering system where you, without shadow of a doubt, are filtering noise and not valid signals.
Right.
Okay, because this is just a soup of frequencies. Okay?
No, 100%. Yeah.
But, okay, I'm going to give you the benefit of the doubt. You've concocted this phenomenal filtering. So let's take noise out of the equation. Let's just say that the noise level is equal now to the factory. Okay?
Not even remotely feasible, but I'll live in your hypothetical world, Tom.
Yeah. Work with me now. We're in the world of Oz. Okay?
Yeah, absolutely.
Okay? Or we followed the rabbit down the hole right now. We're in Wonderland. Right. So there's no noise. Okay? That's gone. Well, let me ask you this. How are you doing the mapping on that 5 picocoulomb signal? You still have attenuation and dispersion. Yeah. Cables are low pass filters by design.
Right.
And you can't control the lengths.
You got to get through all the splices and everything else. And like you said, if you don't have a return signal, you have nothing to work with. So
how are you going to map it?
Yeah.
Particularly when the pulse calibrators that they sell for field applications, typically the lowest settings on them is like around 50 picocoulomb to 100 picocoulomb. I'm sure if you wanted to buy one, to a 5 picocoulomb level, they're available on the market. They're probably, more typically utilized at factories and so forth like that. Right. But again, if you're making that claim, I would like to see the evidence. I would like to see the supporting waveform captured from a field application where you injected 5 picocoulombs. It went, 1 mile and had enough energy to reflect all the way back to your receiver. And you're showing me, the full length of cable with 5 picocoulomb.
Now, are there any other particular instances like we already talked about, the burning up of the cable based on the ground and the soil stuff? You have to introducing acoustic stuff like traffic and stuff like that. I'm assuming based on the frequency you're measuring, just bypassing traffic and stuff could mess up the frequencies inside or introduce some more interference, which would be another thing you would have to filter out, I would imagine, or is that kind of off base?
Oh, it's interesting. Like when I get into the world of like online partial discharge testing, where we're taking these scanning tools into a substation and so forth, your SCADA systems operating up around 900 megahertz start to become interference. Matter of fact, the way I teach a lot of young technicians on how to use the radio frequency detectors to find the partial discharge is we play hide and go seek. They'll be on like a walkie-talkie broadcasting at a certain frequency band. and I have them hide behind gear. And we basically just tune the receiver into that frequency and hunt them down. Okay.
That's awesome. Yeah.
Well, back in the olden days, the way we used to do corona studies and everything in the substations was we would take a radio in and follow the crackling noise sound.
I'll be damned.
It's capturing frequencies.
Right.
Like any radio station, you have to be able to tune into the one you're looking for.
Another thing,
and
right? You're going to have all that
filter, block the unwanteds.
Well, and even then, and that kind of goes to the point of talking about doing a 60 hertz test and getting down to the picocoulomb level. You've got all this residual stuff. And like we've already talked about, there's a porosity aspect to the dielectric as well. And you can only shield out so much, but you're still going to get some of that's going to be filtered in. So how the hell are you going to filter all that stuff out in order to get an accurate test?
Right. But I'm going to give you that benefit of the doubt that, we went down the rabbit hole. We're now
back in the rabbit hole
sipping tea with the Mad Hatter, and it's all feasible. That noise is not an issue in the field. I'm going to give you that. You still have to explain how you're getting across attenuation and dispersion on a low pass filter.
Long runs at that point
long runs
as well.
Of cable.
Yeah.
So you still got to bring that one to the table of how you're accomplishing that level of sensitivity. And even in the IEEE 500, or sorry, IEEE 400.5, another senior citizen moment there. Thank you, audience.
I've had like 3 of those this time. I hope nobody knocks it off.
Even in that document, when it talks about factory-based testing or field-based testing, it even says as a call out in the field-based testing that testing it to factory-level sensitivities is typically not accomplishable in a field environment.
Right.
Because these are real elements that we're dealing with in the field that we can control in the factory. And again, taking the noise out of the equation, giving you the benefit of the doubt.
Right.
I still need to know how you're getting a 5 picocoulomb signal at around 650 to 700 megahertz to travel these extensive distances without attenuating and dispersing to the point that you can't pick it up and you can't accomplish mapping.
Absolutely. Which is the whole point of the damn test in the first place.
Well, yeah. Otherwise, I go to my client, I give him a report and says, "Oh yeah, I discovered 5 picocoulombs on your collector feeder cable. What's going to be their next question? Well, where is it?
Exactly.
It's in your collector cable.
Exactly.
I
can't tell you where, but it's there.
Yeah, replace that 7-mile cable.
Right.
I do business on what I call the rule of handshake. After I give you a service, the next time I come back to see you, I want to be greeted with a handshake and not a baseball bat.
Absolutely. Absolutely. And I think that's a great way to go about it. Now, so with that being said, so would you say the 0.1 hertz testing, does that overcome a little bit more? I know we kind of talked about that and kind of not living in the hypothetical and all that. What's the ideal solution, or is there one?
The ideal solution is in the eyes of the beholder. What is your budget? What type of cable runs, where do we need to hook up the equipment? What's the available power supply to power our equipment? So the ideal answer obviously is in the eye of the owner, the beholder, and everything, because everything in life has advantages and disadvantages and trade-offs. We have to weigh to what makes sense to all of us. So there's no exact answer. What I will say, now that the technology supports sinusoidal VLF as well as cosine rectangular, a lot of the issues that if we were only dealing with sinusoidal, there's another alternative that I can go to that overcomes that obstacle and still provides a cost-effective package. And we haven't even talked about the damped AC. Damped AC is that sudden blast oscillatory, up there in the 30 hertz to 100 hertz realm. Right. Still has the polarity reversals, very comparable to power frequency, correlates well with power frequency testing. So if it's, a surface age cable where there might be semiconductive residues in the void, and I'm worried that my partial discharge inception is not going to correlate to 60 hertz, I now have the cosine rectangular VLF option and I have the DAC option at my availability. Still, both are going to give me a more practical price structure than hauling out the big 60 hertz or the resident supplies and a dedicated vehicle. So one, we're going to find more companies that can offer these services. So you as the owner, when you're shopping around and getting bids, you're going to open up to more bid structure, invite more people, because more players can get involved.
Right.
You'll still basically get what you're looking for. What is the quality, or are there any issues or anything out there? And again, if you're a purist and you have the budget and you have the environment that can take one of these dedicated testing systems, you know what? More power to you. I mean,
Right.
I'm all for testing it at 60 hertz. Let's face it. In the perfect world, we would never have used DC. We would never have used VLF. We would never have used any of the alternative frequencies in a perfect world.
Right.
But the fact is, through time and history, bringing a power frequency test set into the field, and particularly on high capacitive devices like cables, generators, large motors, it's just not practical or cost prohibitive to bring these big dedicated systems into a field environment.
Right.
Hence,
and you would typically want to mount those as a permanent installation by something that's portable, I would imagine, just based on the logistics and constraints. Or are there companies out there that literally bring you out an 18 wheeler with the test set and the generator on board that are huge?
Absolutely. There are companies that have really dedicated, special dedicated
to the
where,
60 hertz
like
testing?
on the high voltage and extra high voltage, they're literally bringing out, the 18 wheeler rig and setting up, with a lot of the elements that, would be used in a factory type situation and everything. When you get down into the medium voltage realm, okay, the trucks don't have to be 18 wheelers, they get, much smaller, but they're dedicated, van or panel truck designed, and housing the equipment in it full time. And you know what? That's awesome. That's your business model and so forth. But, obviously your overhead is still going to be a little on the high side.
You have to have dedicated assets that can't be multi-use, and now you're dealing with that and carrying the overhead.
Again, if that's your business practice, and again, that's your primary business function.
That's your business model.
Yeah, that's totally awesome. But again, for the client, the owner, you have choices. Don't just get taken in by the sales and marketing statement,
right?
Because you're getting the non-Paul Harvey version in a lot of cases. You're getting the segment of the argument that sells, what I want to sell you.
Right.
Okay? Again, what's that old, adage, there's two sides to every argument.
Right.
You're only getting one side. You're not getting the other perspective. So, do yourself a favor, do the research, get yourself a copy of 400.3.
Yep.
I mean, don't take my word for any of this. Get the document, go to section 8, where it talks a lot about factory versus field. The document is the new 2023 release is gorgeous. It really talks, you want to learn more about attenuation, dispersion, signal propagation, the world of physics, okay, of why, these things work or have limitations. This is the document. So, I mean, just don't take anybody's face value word.
Do your due diligence and go out and actually do the research, read the documentation, and then understand what are the salient points and benefits to each individual testing methodology. I mean, based on our conversation, you got me sold on the the VLF with the alternating frequency. Geez, I'm having an old man moment here as well.
The VLF cosine rectangular.
There you go, cosine rectangular.
Yeah, I'm really digging that one.
That makes sense to me. I mean, it sounds, that seems like a pretty good mix of cost effective. But again, there's going to be varying degrees of need and requirement and cost basis and things like that. So to each their own, as long as you do the due diligence to know what else is out there.
Now, for the test companies that are getting involved in this, okay, remember back when we were talking about workforce development, and we had we're talking about the artificial intelligence and the equipment getting so smart and everything.
Right.
Okay. if I'm going to offer any advice out to the test companies that are getting involved in this field, again, do your due diligence and understand what you're getting into. Particularly, understand how to manage your clients' expectations and understand what your deliverable product to them is going to be when the testing is done. Because I will say that almost all of the equipment rental companies that support us testing companies,
your IntelliRents, your A-Rents, and all those bubbas.
Yeah, exactly. Protex, ECPs,
Protec,
et cetera. The list just keeps on going, right?
Absolutely.
They all have these partial discharge systems in their inventory. Now, the lion's share is the sinusoidal VLF versions. No harm, no foul, because a lot of the demand in testing is on acceptance of new systems.
Right.
So I don't have a problem with the PDIV issue because, again, unless they're buying a used cable to put into service, there shouldn't be any semiconductor residues due to past discharges and so forth.
You're literally just doing the acceptance functionality there and making sure it meets still within manufacturer specs. Okay, got it. Let's roll.
So for a test company getting involved in this, before making the large capital investment into a dedicated a system for their use, there's a lot on the rental market. And what also makes it very sexy and attractive is when we read the literature and we find out that that system has an auto mode. Oh, I can rent it and I don't have to think.
I don't have to do anything.
The equipment does all the thinking for me.
To the point that we talked about also in our previous conversation around that same topic. Yep.
So I run a test and I hand a report in, right? And I get paid.
Right.
Why wouldn't I get involved in this business, right? Well, the computer systems, the autos and everything, they're fantastic. Not knocking. They really are really great. But they don't think. They're not the human brain. Okay. The value that you're giving to the client is not in the hardware that you're using. It's the gray matter between the ears of the person doing the work. And one of the things that when you run these tests, one of the things that you have to do is you have to do on the last step, validate all your captured data.
Gotcha.
Because you will capture noise. And they may look like legitimate, PD activity, but you have to go ahead and what we do in the analysis is we look at what we call pattern recognition, where the captured patterns are in respect to the 60 hertz sine wave. So we look at the patterns. We look at the frequency. How many times did we get a strike? Okay.
Gotcha.
Because it could have been just an aberration. It could have been,
one of those external factors coming into play that introduce some random something that's not actually indicative of PD.
I mean, maybe during the test that North American mat flew by and farted, and boom, I got this the signal.
Now you got your 5 picocoulomb readings there.
But again, it's not repeated. It was just like one or two little hits, not repeated or anything. So we look at pulse count. We look at the pattern recognition. We look at the amplitude. And the other is a lot of times too, what is the insulator that we're testing? There are things like PD resistant, PD free. So sometimes, we also have to make a decision, of does this require immediate attention? Can I push this off?
Right.
So let's say that I detected some partial discharge, but it was maybe at 2 times your operating level. The pulse count was relatively low, magnitude was moderate or something of that nature, and it extinguished well before we ever got down to your operating level.
Then probably not going to cause any substantial degradations to the cable.
I may look at that and say, that's not really causing me any real issues. I'm going to get years of good performance life and everything out of it. Now in my overall cable maintenance strategy, in 5 years or whatever, I'll probably do a preventative maintenance test on it. So where does the PDIV now fall? Where does it extinguish? Is it becoming a problem? Or, again, it's way up above where I'm even operating. And oh my God, even if I did have a lightning strike or a surge, I might have a momentary spike. I get, a few microseconds of PD, but once the line stabilizes, the PD is
Not
gone.
a big deal, and it's gone. Yep.
So again, I may still get 20, 30 odd years of life out of this thing. So again, these are the discussions that, when you approach your clients, this is where you put value in your company. Do a little consulting with them on the front end to help manage their expectations.
Yep.
And again, even if they're asking in their bid spec for brand A, feel free to go in there and give them a good technical description of alternate method or whatever. Does this still accomplish your goal? Does it fit a little bit more into making that goal achievable and a reality?
Right.
Again, I've always found throughout my career, consultative style selling is a winning ticket, because the smarter my client, the lower my sales costs, and the happier the client, because they know what they're getting, why they're getting it, and they become that very loyal client.
Yeah, absolutely. And we do the same thing in the recruitment methodology. It's all about being consultative, offering different options out there, explaining the limitations of the equipment or the functionality limitations or whatever it may be, life expectancy. Like you said, you may come out and you may find some PD, but it's still above the standard levels that you would expect. Well, that tells me I can run it for another couple of years, no harm, no foul. And then if you're letting them know that, now you're helping them mitigate their cost concerns as well from that aspect. And truly, so yeah, I'm just echoing your sentiments and saying the exact same thing. But it's highly valuable. It's not
Exactly.
a transactional; it's a relational and consultative approach.
Exactly. So owners, do your due diligence. Don't just take everything on face value. Because, let's face it, whether you're the OEM selling you the hardware, whether you're the service company selling you the service, these are businesses and they want to push their methodology.
Right.
So
because they have a lot of R&D and other things that are tied up in it. And it could be betting the bank on that particular technology.
So they're going to construct their arguments to their favor. Okay. And that's not making them bad people.
No,
okay.
Not at all.
But you want to get the rest of the story. You as the buyer want to know what all your options are so that you can make the best informed decision. Now, you as the service company, do your due diligence. Look at all the different technologies, the pros, the cons. Look at who your base clientele is going to be. What type of environments that, you may find yourself, up against, and make an informed decision on what you're going to invest in. And again, give both sides give the full story, not just your
rest of the story, Tom. It's the
because
rest of the story.
The more informed the client is, if they award you the contract, there's no surprises. They know exactly what they bought. They knew exactly what the advantages were and why they wanted it. They accepted and signed off on the limitations and said, I'm willing to take that because your offering basically delivers what I'm looking for. Right. So test companies, don't mislead, consult, explain, inform the client. Owners, do your due diligence so that somebody doesn't come in there and sell their objective to you that might not be the best for you.
Right. I think that's all salient, and I definitely learned a lot more than I ever thought I would about partial discharge today of shielded cables. So very, very cool tech, and this is just getting into the minutiae, and it kind of covers the variety of testing that NETA technicians or testing companies do throughout, and showing that there is a diverse range out there. And I think the most important takeaway for me, outside of the different methodologies, is do your due diligence. Make sure you have a full scope and understanding of what's going on, and choose whatever meets your cost constraints, concerns, and ultimate objectives. Is that kind of the key takeaway?
Beautiful takeaway. Absolutely.
I love it. Well, brother, we're up to about an hour and 33 minutes. So I think we've delivered some really, really, or you perhaps, I just asked a couple of questions throughout, but definitely brought up some really, really relevant stuff. And for anybody, I know you're a sharer of knowledge, wisdom, information, and work with junior techs and stuff. Where can people reach you or contact you?
Oh, you can definitely find me in the social media realm. Go to LinkedIn, just do a search on Tom Sandri. I'll pop up there. Go to your local post office on the wanted wall. You'll definitely see photographs
Understood.
of me there. Or probably the most direct path. The most direct path would be email. And the email is Sandri, Tsandri, at Vector Powers, abbreviated. So it's VECTORPWRS.com.
Awesome.
And again, I'm used to technicians and different owners and everybody who've come to know me, from conferences or whatever, reaching out to me. I'm always happy to go ahead and answer questions. I mean, it's a benefit to me. I grow my network that way. You grow your network that way, and we all prosper. We all win.
Absolutely, and couldn't agree more. Well, my friend, we'll go ahead and call that a wrap on another great piece. Again, I thank you for taking the time to share your knowledge. I know you were amazingly busy at all times, flying everywhere, going out on site, assisting techs, and doing everything else. So it is truly appreciated that you would take the time to say, just to hop on here and share your knowledge on this little slice of the internet here that we try to share and distribute information that's hopefully beneficial and impactful for technicians and owners and things like that. So again, I thank you, my friend.
I definitely enjoyed it. I got to sit back, a relaxed conversation. It kind of felt like we were at the pub together, just socializing. I got my cigar, have my coffee. I mean, really, really enjoy your platform.
Thank you, brother. I appreciate it. And folks, until next time, Mike out.